Okay, this is going to be a totally disorganized talk for 3 reasons. One, I just got back from Australia. Everybody coming from Australia, raise our hands. Okay, so we've been in planes for 2 days. And then the discussion of this topic has got me to kind of rearrange things as well. Thank you, Faith. So, thinking outside the box, things you shouldn't be able to detect with BGC Argo, but you can. And that's, and Marty says not the box, thinking outside the float, okay? I really want to, so this, while this is, you know, as Yui said, tons of people make Argo work. In particular, I want to acknowledge Steve Reiser. He gave this talk at a talk at the 6th Argo Science Workshop in Tokyo on the scientific accomplishments of core Argo, and he used this diagram to cast his whole talk. This is the sea level variance in color from the sea surface satellites, the frequency of the variance and the wave number of the variance. So signals that are 1 year, you see the annual cycle in that blue line up there. That's the annual cycle of this winter summer sea surface variance. 1 day is down here, and 1 hour down here, and 10 kilometers, 1,000 kilometers, and you know, all the way around the world, kilometers. And core Argo was really designed to work up in that oval at the top. That's what they designed and built the array to do. And he then went through a whole set of explanations of all the things that you can do with an array of floats where the data is intercomparable between floats, and they're all operating in synchrony globally. Things that you never imagined you could do, you can do. And the thing that really got me was I hadn't been aware of this, but beautiful paper by Sarah Gilly at Scripps, deducing the the diurnal cycle of temperature from floats that go up and down every 10 days. How the hell do you do that, right? And I thought, gee, if you can do that with temperature, you should be able to do that with oxygen too. And lo and behold, I'm going to zip down. So changing the structure. Thank you, Faye. I'm going to zip down and go through. And I guess I'm going to have to go back. But the theory. This is a paper that Rue wrote. Data example from gliders at Hawaii. If you want to get, there is a diurnal cycle of oxygen in the ocean due to plant growth. Oxygen goes up in the afternoon, down at night when the plants respire, up in the day when they photosynthesize. And you would think that to deduce that, you've got to like run a glider that's going up and down multiple times over the day. And it does work. That works beautifully. But the other way to get that same signal is not to have one float going up and down, not just once a day, but 3 or 4 times a day, is to have a whole bunch of floats out there, all coming up at different times of the day. And so each float is sampling different parts of the diurnal cycle, right? And then you just take the whole array of floats. You treat the array of floats like one big giant sensor array that's sampling the ocean at different times. And from that variability, you can get the diurnal cycle of oxygen. It is not at one spot, because the floats are not all at one spot, they're spread all over. So you get the global number for productivity of the ocean. It's really the first time that the global productivity of the ocean has been measured. So Mari and I wrote this paper in Nature Geoscience, and then Adam came along, gosh darn it, and I thought about this too, but I just didn't have time to do this, Adam. And wrote a beautiful paper. Not only can you do oxygen, but you can get from the optical backscatter, you can get the growth when the phytoplankton grow. There's more phytoplankton in the afternoon. There's more backscatter in the afternoon. Everywhere in the world ocean, a little more oxygen, a little more backscatter in the afternoon. And you can get the diurnal cycle of productivity from oxygen, from backscatter. And in Adam's case, then you can look at the ratio and you can start to deduce, you know, really interesting things by having multiple senses, which was a point that Yui made this morning about why not just have one sensor on the float. Have multiple ones, okay? And there's another paper in review with Rue and Adam and Robert Isaac. Should be out, I guess, or accepted or something. Again, looking at this diurnal cycling business. You know, and that just, it just comes out. You get this is for the entire northern hemisphere, the entire southern hemisphere, but you can actually go to, you know, reasonable area. You just need a bunch of floats. Adam has a nice analysis of how many floats you really need. It's not one, it's like 20 or 30, you get the number, but with 20 or 30, you can get the global, start to get productivity. So there's a super advantage, all due to Reiser's paper, of all these different things you can do, rather than just the core Argo mission. You can really get to things, and you can run a sustained array for long periods of time. So, okay, diversion back. So now we're gonna go backwards. Sorry, bam, 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 bam. So it's not just the diel structure of oxygen and nitrate, many other things that Argo was never designed to do, and biogeochemical Argo, when we wrote the science and implementation plan, were designed to do, but which you can do if you have a big array. A nice example, Zhao Yang Su, looking at eddies, and also Martin Kornick, also looking at eddies with Argo. Argo is supposed to be doing whole basin scale things, but gosh, you can go do eddies, and how do you do that? So I'm gonna, let's see, show a talk that Liddy Kepler just gave at several of us were in Hobart, Tasmania for a Southern Ocean talk. This is a talk Liddy gave on mesoscale eddies. And the interesting thing is, to do these things, you need, so the signal of eddies, whatever, is all convolved into this basin scale signal. You need one more bit of information to take these out, and that's some other information about, like, eddies, where the eddies are, but that data exists. There are products, Dudley Shelton, and the satellite products produced from sea surface altimetry that just daily maps of where eddies are in the ocean. And you look at float profiles, and so here's an example. That's a float profile, came up in a cyclonic eddy. That's a profile where a float came up same day in a anticyclonic eddy, and that's a profile not in an eddy, right? And statistically, you just accumulate that data, and there's a lot of data. Liddy says she has 594 profiles in eddies, in cyclonic eddies, 670 profiles in anticyclones. And you start to make these beautiful plots of the anomaly of dissolved inorganic carbon and nitrate and oxygen. These are anticyclones and cyclones, and the cyclonic eddies, which are upwelling, have more carbon because of the upwelling, and the anticyclones have less carbon because of the upwelling in it. So this is just distance in terms of the radius of the eddy out from the edge. And so you start to accumulate. It's a different view than normally you'd get on a ship and you'd tow a seesaw or something across the cyclone, across the eddy to map it, right? But now we're just getting a statistical view, and it's, you know, reproducible, and it's great. So you can do that for eddies. Or here's an example of a paper, Magdalena Carranza, Labari, looking at the effect of storms on CO2 outgassing. And again, due to the atmospheric reanalysis models, which just take the weather models, all that data stored, you can map where the storms are, right? And every time a float comes up, you can map if it's in a storm or not in a storm, right? And you can map its distance from the middle of the storm. And so you've got the floats, but you need one other product. In one case, it's sea surface altimetry, the eddies. In this case, it's the atmospheric model of storms. And you've got to write some code that figures out define what a storm is. That's wind speed above a certain velocity and atmospheric pressure below a certain velocity. And you've got the whole, you know, storm map. And so this is Magdalena's paper. It's in review right now. And here are eddies in CO2 outgassing anomaly and so this is coordinates, our distance from the storm center. So 0, and you're going out 1,000 kilometers, the way that the big storms in the Southern Ocean, so you go 1,000 kilometers around the Southern Ocean, and every time you just statistically, accumulate the data. And what you see on the north side, on the equatorial side of the storm, there's more CO2 outgassing because that's where the wind stress is greater. The storms are propagating to the east and the wind is going around. There's a greater stress on the sea surface to the north. Get more outgassing to the north. And you can then, so this is a map of floats and storms, and you get this beautiful assessment of CO2 outgassing. There is more outgassing in a storm. You can actually deduce the mechanisms why there's more outgassing. In this paper, she compares it to what we see in coupled models. The models see more outgassing in a storm, but only because atmospheric pressure is low in a storm. So the ocean partial pressure stays the same, atmospheric pressure goes down, CO2 comes out. It's like uncorking, a champagne bottle. But what Magdalena sees in her data is that not only do you have the atmospheric pressure problem issue, but in the real world, the ocean mixes deeper than the models, and you entrain higher PCO2 into the storm. You entrain more dissolved inorganic carbon. You mix deeper than the models do. And so you increase CO2 due to mixing and lower atmospheric pressure. And she sees like 4 times more outgassing, which turns out to be a very important contribution to air-sea CO2 flux. It's like 20-30% of the Southern Ocean carbon flux due to this enhanced flux in storms. Not something you ever thought you'd really do in Argo. Okay, so, and that's so she can see the signal due to due to the delta PCO2, due to the lower atmospheric pressure, and so on. Anyway, and that is, this is the float, and this is the CESM coupled model. Okay, so now we're back to the diurnal variability. I was supposed to show this is this great paper by Sarah Gilly that Steve Reiser mentioned. You can get the diurnal temperature cycle. How am I doing on?
3 minutes.
3 minutes, okay. So floats give you this beautiful diurnal cycle, and I went through this, and I went through that, and I'm gonna go by that, other than to make the point which Allison made as well. Step 1 in your workflow is QC the data yourself. We're trying to do the QC, but we are not perfect. And if you're using the global data, it extends everywhere in the data system. You should do your own QC. And if data, I think that Adam did his own QC with data. I did QC it's always some weird data in there. If you have millions of data points, sometimes a weird number, these up here where the red cross is, those are bad data. It's gotten through the Argo system, it's flagged good, but it's not. If you have a million data points, 10 probably aren't going to matter. But if you get a whole block of data, which I think this might be up there, a chunk of bad data, you might want to QC that out. You want to think about it, seriously. Okay, let's see. We went through that. That, by the way, is Adam's paper, very nice. So it's using you see the diel cycle both in backscatter and in oxygen. And there's a whole nother story about the fact that floats have to be randomly sampled all different hours of the day. If a lot of floats only sample one at a fix, like noon, you can't use those for this kind of analysis, got to get rid of those. But where I wanted to leave you, this is something that Yui talked about. There's a whole evolving field now of looking at non-photochemical quenching of chlorophyll and relating that to iron stress. This was the paper, Yui's list of favorite papers up here, Ryan Keogh et al. In Science this year. Another paper by Christina Schallenberg, iron limitation drives the globally extreme fluorescence chlorophyll ratios in the Southern Ocean. And they're all driven by the non-photochemical quenching. NPQ is when a phytoplankton gets too much light, it doesn't want to put that extra light energy into its photochemical photosynthetic system. It is able to radiate that light energy as heat and it doesn't fluoresce it. So NPQ, the phytoplankton in bright in the daytime in light will not fluoresce as much. We hate this if you're trying to use chlorophyll to use fluorescence to measure chlorophyll. That is noise, but one person's noise is another person's signal. right? And so here's an example globally. So the same process that we use to deduce oxygen or backscatter data, I can get the diel cycle of chlorophyll. That diel cycle is not chlorophyll growing in the day, it's non-photochemical quenching. Here, this is all the globally, and I can do it. I can run anywhere in the world. I got code. I can do anything. You can do it versus depth. So at the surface, there's a lot of light. There's a lot of quenching. If you look down at this is 80 to 100 meters. There's not much quenching because there's not much light. And you can do the same thing as the Southern Ocean seasonal cycle. In the summer, there's a lot of quenching. January, February, March. In the winter, there's not much light. There's not much NPQ. That's all really related to iron stress. And so you can, for example, look, this is 35, all of the Pacific Ocean, 35 to 45 south latitude, and here's the Atlantic. We generally believe the Atlantic has got more iron in it, right? Because wind dust blowing off Patagonia. And the NPQ, this is seasonally again, but on average in the Pacific Ocean, the average NPQ is 1.7, and in the Atlantic it's 0.7, which kind of makes sense. There's less iron. You would think there's less iron stress in the Atlantic Ocean because there's more iron. And in fact, if I went back, that's the whole point of these beautiful papers by Ryan Keogh and Schallenberg. NPQ gets relieved with the plankton have more iron. They can deal with the light. They don't have to get rid of the light energy as heat. And so this is a workshop in analyzing data. I'm trying to equip folks, like there's a phytoplankton productivity group. You could now map NPQ globally. These papers, Ryan Keogh et al. Schallenberg, they use what we correct the data for what we think NPQ is. We don't actually measure it, we correct it for what we think it is. And they use the difference between the raw data and what we think NPQ is. But this is actually a measurement of NPQ, much as the diel cycle of oxygen is a measure of primary production, whereas satellite numbers are sort of a model. And these guys are using them. So you can actually take the float data, I would argue. Some group here might want to, map the NPQ. To do technically what is done here, you want to have irradiance normalized NPQ. So Ryan Keogh et al., they only used floats with a radiometer and a fluorometer. Not many of the floats globally. There are very few radiometer floats globally. But as I say, you need one other product. There are satellite products of light penetration in the ocean. And, you could, and it, just as we see here, the difference between the Pacific and Atlantic, you could model the light. You can get the satellite light penetration 0 minutes, and I'm done. That's it. Oh, no, I'm not done. Sorry. The last thing, the other thing, this is something Mari and I have been working on. The other thing is that there are other products in the data. One person's noise is another person's signal. There are funny baselines in the UV nitrate system. We can now get nitrite out of the funny baseline. So this is a float in the OMZ of the Eastern North Pacific, and that's the nitrite versus the 1.5 years or so of data watching the nitrate get produced and go away in the system. It's starting to be I feel like we're on the frontier because it's a machine learning method.
No.
Yeah, so.
Never be machine learning.
Anyway. What, pardon? Yeah. Anyway, okay, I'm done.
We have one question.
Yeah.
Have you looked to see if your measurements of NPQ there match with, I guess, the assumptions made the NPQ correction?
And the answer is no, I have not looked. That's a good question. That would be actually another kind of cool use of the data, because you can, find out if what we're doing is correct. But I have not done that. Good idea.
Thanks.